So you'll already be familiar with paper chromatography, which is used to separate like felt tip pens or food colouring, that sort of thing. And we can now look at thin layer chromatography. So if you don't already have these notes, it's best that you write them down and listen carefully to this section of the video. So what we've got here then, we've got thin layer chromatography. So thin layer chromatography is often abbreviated as TLC, thin layer chromatography, TLC. So essentially this is often used when you've got a polypeptide and you hydrolyze it, in other words you break it up into the amino acids that it made from, and then you get this plate, and this plate here has got a coating of silica on it, silicon dioxide, SiO2, and you put it in a container, and then you add the solvent up to a depth of about 1/2 centimetre, and then you put your spot of a mixture of amino acids that you want to work out which amino acids are in that mixture, and then what you do is you leave the solvent to rise up the plate, and before the solvent gets to the top, you take the plate out of the container and you mark what we call the solvent front, which is the end solvent line here, and then you'll find that you can't actually see the spots. So we spray the plate with a developing agent, which we call an anhydrin, and that turns the spots from invisible to purple. Or as an alternative to spray it with an anhydrin, we can shine the plate under UV lamp, and then you can see the spots. And what we do is we measure the distance that the spots moved, and we measure the distance that the solvent moved, and we divide the spot distance by the solvent distance, and we get the RF values, which don't have any units, and we can compare those RF values to pure amino acids in the same solvent, and that essentially is TLC. Now, what we also need to know about is column chromatography, so we're going to discuss that now. So column chromatography uses a powder such as silica or resin as the stationary phase, and that's packed into a narrow tube called the column. So I'll draw a little diagram to show what that looks like. So we've got our column here like this, and in there you've got your silica powder, and that's the stationary phase. So you pack in this powder at the stationary phase. That's the equivalent to the silica that's on the TLC plate. And then what you do is you put the solvent in there as well, which is the mobile phase. And then what you do is you put your sample in the top, and everything runs down the column, and then the components of the mixture move out at different rates depending on the affinity to the mobile phase, the solvent, compared to the affinity to the silica, which is the stationary phase. And the different parts of the sample are collected at the bottom here. So the one which comes out first would be the part of the sample which has the greater affinity to the mobile phase, and a sample which comes out next would have slightly less affinity to the mobile phase, and maybe more so to the stationary phase. And then you get these samples out over time, and then you can analyse each sample like this, and then you might work out that perhaps there might be 2 amino acids in total. So you might get one amino acid out first, and then second you might get two different amino acids. So you might have the same amino acid coming out second, plus another one, and then by the time you get your third sample, you've got all of your first amino acid, and you end up with just one compound in there. And then you can analyse those samples to find out what amino acids actually are in there. So that's column chromatography. And the next one is gas chromatography. It's sometimes abbreviated GC for gas chromatography. And this technique is the one that's used mostly in modern analytical techniques. And basically the stationary phase is a powder coated with an oil. It's either packed or coated into an inside of a long tube about 100 meters long that's just coiled up inside a machine. So what happens is you've got this machine here like this, and then you put the sample in the machine like that, and the sample goes around inside like this in this long tube, and it eventually comes out and hits the detector, and it's pushed along the sample via a carrier gas. So in this case, the stationary phase is a powder inside this tube. And the mobile phase is this carrier gas. We often use something like nitrogen as the carrier gas, and the reason why we use something like nitrogen is that it's unreactive. We don't want the carrier gas to react with the sample that we're trying to analyse. And depending on when it hits the detector, will depend on the affinity between the stationary phase and the sample, or the sample and the mobile phase. So if the sample has got a greater affinity to the mobile phase, then it will hit the detector first. And if the sample has a greater affinity to the stationary phase, then it will spend longer inside the GC machine and it'll hit the detector last. Okay, so it's all about time, this one. And we call those times to hit the detector the retention times. So each part of the sample or each substance in the sample will have a different retention time after you've injected the sample into that. So various types of detectors are used, including ones that measure the thermal conductivity of the emerging gas. And what can also happen is we can get like a graph from this detector as well. So you might have on the x-axis here retention time. So the longer the sample is in the GC, the greater affinity it does have to the stationary phase. And then you have the signal strength up here like that, and then you might get a peak like this or like that. And what does that tell us? It tells us that there's 3 substances there that's been analysed in the mixture. It tells us that this one here is the most abundant, that's the second most abundant, and that's the third most abundant. So this one here has got the lowest retention time, so the one with the least abundance has the greater affinity to the mobile phase. That's why it comes out first. This one here has the, I suppose, a medium level abundance, and that there would have the greater affinity to the stationary phase. That's why the retention time is much much later. Okay. Now, this is an analytical method for separating substances. In GC is extremely sensitive, so you only need a small amount of sample, and it can separate minute traces of substance. So that's really useful for that. And it's best known for testing athletes' blood or urine for drug taking. And the identification of a component is done by matching its retention time with a known substance in the same conditions. And then what we can do to finally confirm what the actual substance is, we can not only just record the retention time to a known retention time of a known substance. What we can then do is once this substance here hits the detector, we can send that to a mass spectrometer. And then when this one hits the detector, we can send that one to the mass spectrometer. When that one hits the detector, we can send that one to the mass spectrometer. And we know that mass spectrometry is often abbreviated MS, like that. So we can actually get machines which have got a gas chromatography part and a mass spectrometer part in one machine. And we'll call that GCMS. So GCMS stands for gas chromatography, mass spectroscopy. And it's essentially two techniques in one. And the mass spectrometer is used as a detector for the gas chromatography system. As each component of the mixture comes out of the gas chromatography column, the time it's taken to pass through the column, its retention time is noted, and then each component is fed automatically into a mass spectrometer, which enables the compound to be identified either by its fragmentation pattern that we know about, or by measuring its accurate mass. That's obviously to more than one decimal place. Okay, so there's several types of chromatography, just to summarise. The first is TLC, thin layer chromatography. We've got column chromatography, gas chromatography, and finally GCMS, which is gas chromatography, mass spectroscopy. Just so you can see the bottom bit there, I've just missed it off. This measures its accurate mass, just if you couldn't read that. That's it.